So till now, we have studied the rectifier circuit, the capacitor filter circuit. We have seen its waveforms. We have learned how to simulate the rectifier capacitor filter circuit. We now have to do one important activity, which is designing the components. You have only two types of components. One is the diode, rectifier diode, and the other one is the capacitor. So these two components you will have to rate such that they will be able to handle the electrical stresses and the thermal stresses. In this course, we will discuss about rating for the electrical stresses like the current and the voltage stresses. However, the thermal stress calculation will be another course in itself. So therefore, it is out of the scope as far as this course is concerned to calculate and rate the components for thermal stresses. There is another point which is also there while you are designing circuits, that is to design for life. This is also out of the scope, designing for a given MTTF or MTBF, mean time to fail. However, keep that in mind that these are aspects that you will have to consider when you are designing a practical circuit. In this course now, we will look at how to design for the thermal, how to design for handling the electrical stresses.
We are now back again to the whiteboard where we have the waveforms. We had seen these waveforms earlier. This is the output voltage waveform with the ripple. VC, what we call VC is the output voltage waveform across the capacitance. I naught is the load current. We have shown the average value of the current. There will be a small ripple which will have the similar shape as that of VC divided by R. This green waveform is that of the current out of the rectifier, as we saw, and we need also to define few more parameters which we will do now in order to do the calculations for the values of the capacitance and the diode ratings. Now we know this is half the wave shape of the full sinusoid, so this must be having an angle of pi. Remember that this is whole 2 pi and this much is pi, which means t by 2, period by 2. Then another parameter that we will define is the conduction period, the period for which the diode conducts, and we will name it as alpha. Of course, from this point to this point is also pi, again repeats every cycle. Another variable to define is the peak to peak ripple. So this is the peak to peak swing of the output voltage, and therefore we can call that one as the peak to peak ripple. This definition IM is the peak current that is flowing out of the rectifier as shown here. You see, normally when we are rating or designing the components, there is not much that we would get by trying to calculate exactly the nature of this curve, because we need to anyway give some safety factors and we will normally be overrating the devices. If you consider this green rectangular box, if the current wave shape were something like that, if you design your components for this flat topped green rectangular pulse, then definitely it will handle the inner shape, the shaped pulse as it comes out of the capacitor filter rectifier. So therefore Normally in design practice, what we do, we use the engineering judgment here and say that for rating the devices, we will design the devices to handle this flat top, complete flat top rectangular pulse. Much easier to design for that. And if we design for that, it will definitely handle this shape of current. So that is what we would be trying to do for. This is the current wave shape that we will assume for design, only for design purposes, not for any analysis. So now we shall define one more variable called V naught. V naught is actually the average value of the output voltage Vc, which you see at the capacitance node. So if this is the peak value and this is the min value of the ripple, this plus this divided by 2, the average value will be V naught. So this would be the average value of the current, the average value of the voltage is given here. Two more variables, which is the peak value that the capacitor will take, Vm1, and the minimum value it will discharge to Vm2 in the steady state. So using these variables definition, we shall now calculate what should be the value of the capacitance and also what should be the value of the currents that should flow through the diodes and such. Now for this to write down the equation, it is now better for me to use the writing board. So I will go to the writing board and start writing the equation so that you will be able to follow me. So I have with me the same waveform figure with all the parameters named here with me, and we shall use this for writing the equations, design equations. Now first off, let us calculate the value of the capacitance. Let us note down, write down what is it that is given to you for design purposes, the specifications. So the specs that are given to you are the following. Specifications. One of the things that are given to you would be what is the value of V naught, ripple spec, this will be given to you. It will be given to you as peak to peak ripple variation, delta VR as we have marked. Then what else that would be given is we will have the power P naught, output power, we also have the input spec, now the input voltage has two parts. One is, see, you would probably have something like 230 volt RMS, which implies 230 root 2 peak. This would be your Vm. But it is not just that. Your input voltage will swing from place to place, from 180 degree 180 volts to 270 volts. So plus minus 20%, plus minus 30%. These kind of swings you will find in a real voltage mains grid. So you should also specify the input voltage tolerance So this is generally given like 10% or 15% of your nominal value. So it will vary from minus 10% to 30 volts RMS to plus 10% to 30 volts RMS, which means 230 volt plus or minus 23 volts, things like that. So this tolerance has to be given. So let us say we'll call it as percent tol as the variable. And then of course you need to have the frequency. The frequency, supply frequency is known, it is always 50 Hertz, at least in our country, or you need not bother much about that. So these are the specs that are given to you, these are the specs that are there with you. Using these specs, we have to now arrive at the value of the capacitance C. That is our first job. Let us start at this point. Let us see what is happening at this point, or shall we come down here, corresponding point. So at this point, the capacitor has an energy half CVm1 square. And from here to here, the diodes are off. Likewise here, from here to here, the diodes are off. Capacitance is doing only the job of discharging into the load. So from here to here, it has discharged into the load, nowhere else, and it has reached a lower energy level of half C Vm2 square. So what has happened to all this energy lost from here to here? It has gone to the load. So that is our starting point that we will use. So let me mark here, it is half CVm1 square, and here it is half CVm2 square. What is the difference? So half m1 square minus half CVm2 square goes to the load, and it is actually not for the full pi period, it is for a period of time pi minus alpha. So for a period of time pi minus alpha, capacitors only discharge to the load. So with a duty ratio of pi minus alpha by pi, P naught amount of power is being put. So during that time, V naught into I naught, that much amount of power is being put for a period of time T by 2. So if you look at this equation, pi minus alpha by pi into T by 2 is the weighted period, into P naught the power put to it. So this is actually the energy, watts into time, watt seconds. So that is the energy, the amount of energy that you see here, half C Vm1 square minus half C Vm2 square, that is put into the load. So let us simplify this. Half C Vm1 square minus Vm2 square, which is pi minus alpha by pi P naught by 2 F. F is the supply frequency. Now this can be split into C Vm1 plus Vm2 by 2 into Vm1 minus Vm2. So this is actually a square minus b square form, a plus b into a minus b. Now this is nothing but, let me move the screen up. This is nothing but V naught, the average value. This is nothing but delta VR. So therefore we have C equals pi minus alpha by pi, P naught by 2f, V naught to delta VR coming in the denominator. But P naught itself is V naught into I naught, so V naught and V naught will cancel, and therefore you can write the value of C as pi minus alpha I naught by 2 times supply frequency into delta VR. So this is the value of the capacitor that you will have to put in order to get this particular ripple and for this particular load current. However, you should note that there are few other variations that can come into the picture. You should calculate for the max value of I naught. So that if you calculate for the max value of I naught, the value of C would be sufficient to handle that. You should also calculate for the ripple that is minimum. So for the minimum ripple, I will get a higher value of C. So once you have taken care of the worst case condition for minimum ripple, maximum value of I naught, the value of C will hold good. Another very important criteria that you will have to take into account while you are putting the value of C in a real circuit is when you buy an aluminum electrolytic capacitor, it has a very large tolerance, minus 40% to even 100%, those kind of tolerances. So normally what you calculate and then what you buy and then actually measure can have a very large and significant variation. So normally what is done in practice is once you calculate, let us say you get some 15 microfarads or 10 microfarads, you will take 3 times that value, so 30 microfarads, and put that value. So that even if even the capacitor that you have bought is minus 40% down, it will be able to handle these kind of variations. So this is how you calculate the value of. Let us now calculate the RMS current that is flowing through the capacitance, because that is one parameter which we need to calculate because that will indirectly affect the heating of the capacitor. So to do that, let me go back again to this conduction period, that is when the current is flowing. This alpha time is the period which during which the diodes are conducting. Do we know this value of alpha? We know this value of peak Vm1. This is a cos wave from here. So Vm1 cos of alpha will be Vm2. So we know Vm1, we know the ripple, we know Vm2, and therefore we should be able to know alpha. So how we get that is like this. I will use the blue ink. Vm1 equals, Vm2 equals Vm1 cos alpha. Alpha equals cos inverse Vm2 by Vm1. Vm1 is known which is Vrms value into root 2. Vm2 is known from the spec, which is Vm1 minus delta Vr. All these are coming from the input spec. Then, once you know the value of alpha, you can calculate the current that is flowing through the capacitance. The current that is flowing through the capacitance, now as I said, we are going to make this rectangular approximation, and you have to make use of the condition that the average value of the current through the capacitance is always 0 in the steady state. So this is the area that is the charge up of the capacitor when it is conducting, when the diodes are conducting. When the diodes are not conducting, capacitor is discharging, and the area is this. So we know that this is I naught, and therefore this would be I naught into pi minus alpha by pi into T by 2. That is that area, and this area of course is Im minus I naught alpha by pi into T by 2. So this T by 2 is added so that this is the charge and this is the charge. So if you remove out the T by 2 just to find out the RMS value of the current, so I see RMS is root mean square. So for the positive area, Im minus I naught whole square with a duty cycle of alpha by pi plus I naught square pi minus alpha by pi whole things in the root. So this would be the RMS value of the current that flows through the capacitance. That this RMS current square into the ESR value of the capacitor will give you the heating effect within the capacitor. So this may be useful, especially when you want to do thermal management and thermal design. So once you know these, you will be able to specify the capacitance. So the capacitance can be specified as follows. We know the value. The C value is given by the equation that we just now derived, I naught by 2 F into delta VR. So this I naught you should take I naught max, maximum possible I naught that flows through that, and the minimum value of delta VR min. So under these conditions, what is the value of C that you would get? This variation, why I am mentioning this variation is that the input voltage varies from a minimum value to a maximum value. So find out the delta VR min or whatever the worst case condition and then plug these in. Now the capacitor voltage rating. So the max voltage that the capacitor will ever see will be Vrms into root 2. This is Vm Now VM itself could be swinging to the upper end because of the tolerance I said. 1 plus percent tolerance value, whatever, 10%, 20% by 100. So this would be the maximum value that the capacitor will see. Of course, you also have the IC RMS rating, as we just now saw, Im minus I naught whole square alpha by pi plus I naught square pi minus alpha by pi. So this would be the RMS value. So with this, and then you can say the make type, electrolyte type would be aluminum electrolyte. We don't normally use tantalum. So this would complete the electrical design of the capacitance. Now for the diode. The diode, if you see, when the diodes are off, they would see a maximum voltage, the peak inverse voltage, would be Vrms root 2. So if it is 230, it will be 230 into root 2, 325 volts. To that you give the extra, the tolerance swing for that particular place. This would be the max. So when you choose a diode, you have to choose a diode which is definitely having a peak inverse voltage rating much greater than what you would calculate using this formula. There are two other values that you need to calculate for the diode. One is the average ID average and the ID maximum. So ID maximum is same as the current, the peak current that is flowing through the rectifier. So the ID maximum will be same as this. This is ID maximum Im. Average value through the diode will be, you see that through every diode it flows through alternate cycles. So through D1 and D4 it will be through this. D1 and D4 again it will flow in the next yellow half cycle. D2 and D3 it flows here, and D2 and D3 it will again flow in the next blue half cycle. So therefore the average for this is Im, duty cycle will be alpha by not pi but alpha by 2 pi, because this repeats every 2 pi. So for the diode we can easily find the average in the following manner. Im alpha by 2 pi. This would be the average current that flows through the diode, and when you choose the diode it should have average current rating greater than this, and Im itself is the peak current rating which is flowing for a very small period around alpha for this kind of a pulse approximation. So like this, now you have the diode rating and you also have the capacitor electrically designed, and these values can be your guiding values for you to choose these devices. So what you can do is that we can put these equations into a script file, so that when you want to do an iterative design, you keep changing the specification and then you keep checking things out, and probably you may not get a particular component and then you may want to change few things. So it is good to put them in a script file, like something like Octave or MATLAB. So we will be using Octave script file, and run the script file repeatedly to see what are the design values, so that we don't have to manually calculate these values time and again, which will lead to boredom. So I will now show you how to put them into a script file and thus automate the design process. I shall show you now how to make a sample script for designing the values of the components. So this is our folder dialog. We'll go into DC folder. I have already created a sample here. So this is the M file. I will explain to you. I shall keep it on to one side. At the same time, I would also like to open Octave. I will open this Octave. I shall keep this onto one side, maximize the space, so I have the workspace here. So it is like this. Let me go into the same folder here. Okay. The way I have already written it so that we don't waste too much time. You have to classify your script into three parts. The syntax is very similar to similar to what you would do in MATLAB. It is also having an extension .m file. You have the specification of the circuit written first. Then you proceed with the calculations. All these are calculations, and then followed by display. This is what you would like to display at the end of the day after you finish the calculation. So keep it into these three parts. So for the specification, what is it? This is where you will change for doing iterations. All these calculations are based on these variables. We have specified I have used appropriate variables here because I cannot use subscripts and superscripts. So VI RMS is the input voltage, the tolerance, I have given 20% tolerance. VR is the peak to peak ripple voltage of the output, mains supply frequency, and the power, P naught. And the calculations, you first try to calculate what is the minimum value and the minimum value of the peaks and the maximum value of the peaks, so that you can get the worst case condition. Go through these equations just like we discussed, but I have now used the tolerance values also. Similarly, you will get two values for alpha min, alpha max. Choose the max value of alpha for calculating the value of C. Then here to calculate the voltage that the C will see, the output current, max output current, the capacitor RMS value, and then the diode selection, peak inverse voltage value, ID, average, and the RMS value. Then finally the display. I have used the fprintf statement. One I have used so that it is put onto the display standard output. You could put it to a file also, and this is just like your C syntax: specifications, output power, capacitor selection values, and diode. So these are the parameters that you would like to. So this I will also upload it into Google Drive so that you can have a look at it and then try to make your design script files along these lines. So you go into the Octave workspace. What you would do is just run the script file. So we know that the name is rect_filter.m. You just do that, rect_filter. Don't give the .m extension, just run it. So you will see that this gets executed. So probably it may be good to clear the screen before you. So save that. So let me do that execution once again. So yeah, the specifications, this is the output power, all those things, and capacitor selection values, 114.95 microfarads, so on and so forth. The diode selection and things like that one. I have multiplied here by 1e6 so that I can express it in microfarads rather than having a very long floating point number here. So this way you can keep doing the iterations any number of time, change the power value, make it 1000 watts, and then rerun the script. So you will see things changing, and then you can keep experimenting with it, and then go back to the simulation, plug in the values, and see what are the values that you would get. So this would give you a lot of insight into the rectifier circuit, rectifier filter circuit itself. So this is how you would go about analyzing and designing the two important components in the rectifier filter circuit, which is the diode and the capacitor.